Hello everyone, good afternoon. Hope all of you are safe. Welcome to the webinar by Department of Electronics and Communication Engineering and IEEE student branch of St. Joseph Engineering College, Mangaluru. We are happy and delighted to host the third webinar of our ECE series. Today's webinar is on using predictive modeling for computationally efficient early detection of pathological neural oscillations related to motor deficit in Parkinson. This is by Mr. Ramesh Perumal, research scholar, Neuroengineering Lab, National Tsinghua University, Hsinchu, Taiwan, Senior Engineer, IEI Integration Corporation, New Taipei, Taiwan. And before we start, I just want to tell some housekeeping rules. Your mics are muted by default. Please use chat box for any queries and questions. If you have any questions, we will be taking it up at the end of the session. Make sure that you post the questions in the chat to me. That is, I'm the host of this session. So make sure that you post all the questions towards me so that I can, during the Q&A session, I can put it forward for the speakers. So you can post anytime during the session, and all the sessions questions will be answered during the Q&A session. The slides of the speakers will be made available to the participants based on the speakers' discussion. The recording of the webinar will be available on SJEC YouTube channel in a week's duration. The webinar is purely on gaining knowledge and self-improvement, but we cannot 100% guarantee that without doing any kind of assessment, which is difficult in this mode. Hence, please do not ask for any certificates. It will not be provided. Feedback link will be shared at the end of the Q&A session. Please fill it. It will be doing our future webinars. So with this, now I request our head of the department, Dr. Lakshmi, to welcome the gathering. Over to you, ma'am.
Thank you, Keith. Can you hear me? Hello? Yes. Good afternoon, all. I'm very happy to welcome you all for the third webinar of ECE department on using predictive modeling for computationally efficient early detection of pathological oscillations related to motor deficits in Parkinson's disease. We have recently set up a biomedical electronics research lab in our department with an objective to motivate our faculty and students to do research in the field of biomedical engineering in collaboration with Father Muller Medical College and Research Center, Mangalore. The topic of today's webinar is significantly related to the current trends in biomedical research and will definitely give more insights in this area. Today, we have with us Mr. Ramesh Perumal, Research Scholar, Neuro Engineering Lab, National Tsinghua University, Hsinchu, Taiwan, and a Senior Engineer, IEI Integration Corporation, New Taipei, Taiwan, to enlighten us on early detection of Parkinson's disease. On behalf of management and staff of St. Joseph Engineering College, Bangalore, I welcome you, sir. I would like to welcome Dr. UC Niranjan, Director, Manipal.net, to this webinar. Welcome, sir. A cordial welcome to Dr. Jagdish Bhatt, Associate Professor, ECE Department. Welcome, sir. I'm thankful to you for identifying a good speaker to this webinar. Also, I would like to welcome and thank Mr. Keith Fernandez and Ms. Rashmi H, IEEE SJEC Student Branch Coordinators for arranging this webinar. A warm welcome to all the participants, and I'm sure this webinar will help us to understand the various concepts required for early detection of Parkinson's disease. Thank you.
Thank you, ma'am. Now I request Dr. Jagdish RB, Associate Professor, Department of ECE, to introduce today's speaker to the gathering. Over to you, sir.
So, good afternoon, everyone. I'd like to introduce Mr. Ramesh Perumal. Mr. Ramesh is currently a senior software engineer at IEI Integration Corporation, Taipei, Taiwan. And also, he's a research scholar at Neuro Engineering Lab of National Tsinghua University, Taiwan. Earlier, he had worked as a senior research fellow at Statistical Institute, Bangalore, and as a program analyst at Cognizant Technology Solutions, Chennai. He holds ME and MS degrees from Anna University and Manipal University, respectively. With this, Again, I extend a warm welcome to you, sir.
Okay, sir. Thank you. So over to you, sir. I'll just make you the presenter and I'll stop sharing my slides. Yes, sir. You can start sharing your slides. Yeah, please go ahead. Yes, it's visible. Yeah.
Thank you very much for the welcome note and the brief introduction by Jagdish. And thanks a lot for introducing me to this webinar. It's been a great pleasure to share some of my research findings that may be useful to you in future or I'm very sure that this kind of situation is very difficult to manage, and I'm really happy that you have initiated great job by doing this webinar. Yeah, I hope it would be useful to you. Let me start my my research findings. I will be I'm going to discuss about how we can design algorithms for detecting pathological oscillations from the deep neural recordings of brain. If the algorithm concept is very simple, I'm sure everyone might come across this topic during their undergraduation or post graduation. But my main intention is to show you the motivation towards finding the problem, because for every research problem there may be numerous solutions, but we need to identify the right solution based on the target device and the performance and the required performance metrics. So this is my agenda for today's talk. It's about I would like to introduce the various methodology for detecting the signals, non-stationary events in the signals, in the signals, and going to show some simulation results and some direct applications which might benefit Parkinsonian patients. This introduction session, I would like to brief about Parkinson's disease, its impact, and the available treatment options, and the best treatment options among the available treatment options. Parkinson's disease is the second most neurodegenerative disease in the world. It affects more than 10 million people worldwide. The Parkinson's disease is caused by the loss of certain types of neurons in basal ganglia. That is called dopaminergic neurons. These neurons are essential to control the movements. I mean locomotion, locomotive movements related to maybe voluntary or involuntary movements are controlled by these dopaminergic neurons in the basal ganglia. So, due to the loss of dopaminergic neurons in the basal ganglia, it results in imbalanced locomotory movements. So this is the root cause of the Parkinson's disease. But the problem is there are many reasons, many causes for this Parkinson's disease. One of the dominant cause is found to be the loss of dopaminergic neurons, and you could see the numbers here. Of course, now we are living in this in a situation where we are very well aware of the virus. The count is going very higher, and more than 1 crore people have been infected by this coronavirus. But this is, you could see, this is not a seasonal disease. This disease has been in existence since 1817. So you could understand how many people have been affected in the last 2 centuries. The number of victims in Asian countries is about 6.17 million. It's projected to be 6.17 million, and you could see the prevalence rate here. One of the very important characteristics is that it is highly it demands more money or financial. The annual cost of medical services, you could see 5,99,547 Taiwan dollar. Sorry, 59 lakh 5,99,547 Taiwan dollar. $1 Taiwan dollar is about some 2 rupees or 2.5 Indian rupees. So So here I'm going to show you some of the symptoms faced by Parkinson's disease patient. The cardinal motor symptoms of Parkinson's disease are related to movements. Majority of the symptoms are related to movements. Of course, it has some non-motor symptoms as well, but majority of the motor symptoms include the difficulty in initiating the movement, slowness of movement, or more involuntary movements. These are the different important motor symptoms of Parkinson's disease. Here you are seeing watching a Parkinsonian patient who find difficult in holding his posture or in walking. So Parkinson's disease is named after the physician James Parkinson, who first described the symptoms of the disease in humans in this research note, and assumed the sacking palsy. Initially, it was named as paralysis agitans. Then Dr. Jean-Martin Charcot renamed this disease as Parkinson's disease to honor the contributions of James Parkinson. The cardinal motor symptoms of bradykinesia, that is slowness of movement, resting tremor. That means, tremor means it's a series of involuntary rhythmic movements, and rigidity and postural instability. They find it very difficult to hold their posture. This diagram depicts the symptoms of Parkinson's disease. It was drawn by Dr. Jean-Martin Charcot. Here it clearly describes how the Parkinson's disease patient find it difficult to hold their posture, and their gait problem. Gait problem means like they find it very difficult to manage their walking movements. It's also very important. And these are the available treatment options include surgical procedures. For example, in previous in older days, like they removed a tiny portion of the brain region, infected brain region uh, by surgical procedures, and also the dopamine agonist therapy. There are several treatment options available, but among those options, deep brain stimulation is found to be most effective due to several reasons. I will explain in the next slides. Here, I'm going to show you the principle of deep brain stimulation. Basically, deep brain stimulation involves stimulating the infected brain region, by electrical, current pulses, so that it resolves some of the movement deficits such as tremors or bradykinesia of the Parkinson's disease patients. This animation shows you the concept of deep brain stimulation. It's called open loop DBS, because the stimulation happens continuously during the treatment of period. So you could see, so it requires a surgery as well. During the surgery, the electrodes are implanted into the target brain region, and you see this is the pulse stimulator. It can be placed either in the shoulder or under the skull. So by this principle, the current is passed continuously to the infected brain region, and it helps to relieve some of the motor symptoms, especially the motor symptoms of Parkinson's disease. You could see the current flows continuously in this treatment option. This treatment is found to be the most effective among the available treatment options, and especially it is more suitable for advanced Parkinson's disease patients. So this video is going to show you how the deep brain stimulation controls the tremors. Actually, here you're going to watch a patient who is suffering from tremors in Parkinson's disease. It's one of the characteristic motor symptom of Parkinson's disease. So here you will see how the DBS controls the tremors instantly when it is applied. During the first portion of the video, the DBS, the pulse stimulator is off. Then it is turned on to show the effectiveness of DBS on the tremors. Now they're going to switch on the DBS pulse stimulator. Actually, the tremors are well controlled. Not only tremors, bradykinesia and other movement disorders, movement deficits are well controlled by deep brain stimulation compared to the medications, conventional medications. So you can also see a global market for the DBS devices. The numbers are huge and have very good business in the globe. And only very few companies they're in this business, like Medtronic and Boston Scientific are one of the very big companies in this DBS market. So here you're seeing the pulse stimulators used in the deep brain stimulation. So you could imagine the size of the stimulator. It should be compact enough to be placed under the skull or inside the or under the shoulder. So basically, they are fully implantable devices, meaning that they are going to be placed inside the body. So it demands lower power consumption and smaller size. These two criteria going to make a huge impact in the selection of algorithm for the to automate this procedure. So this is a set of pulse stimulators from St. Jude Medical Incorporation, and the DBS kit is available with it includes the pulse stimulator and also the leads, and also apart from that they will be given a programmer. It's like a like iPad or something like that, and you can also they'll also give a proprietary software you can install the laptop. It is used to collect the data from the device, and also you can change the parameters, stimulation parameters in the device, so that it is by telemetry. It can be controlled remotely. The device can be stimulation parameters can be controlled remotely in the DBS treatment. So, of course, DBS is found to be the most effective solution for treating advanced stages of Parkinson's disease. But we should also see the other side of continuous electrical stimulation. I already highlighted the point in deep brain stimulation. The electrical stimulation is continuous. It continuously hits the infected brain region. So, due to the continuous electrical stimulation, it results in disrupted gait. That means that they find it difficult to. It also induces some other neuropsychiatric as well as movement disorders. They find it difficult to manage their walking position or something like that, and impact cognition and the decision making and learning. And these last three steps or three points are very important. It demands more power consumption because the electrical stimulation is continuous. So obviously the battery life may reduce. Of course, there are some research efforts to make the rechargeable stimulator. So when the battery life is low, definitely we need to go for a battery replacement surgery. Of course, the surgery is very critical. So it's a very important point that affects the in the negative side of conventional deep brain stimulation and reduced therapeutic efficacy. So if brain has the power to adapt to any external stimulus. Due to continuous electrical stimulation, the neuronal networks just learn to adapt to the stimulation parameters. So after a period of time, the effectiveness of the DBS on the symptoms might be reduced. It is reduced. It is put in several papers. So the brain region adapts to the constant stimulation. So in the long term, this DBS is found to it may not be effective for due to this plasticity. This is called technical plasticity of the brain, and moreover, the patient needs to visit the doctors to study the condition and brain response, and the physician directly manually adjust the stimulation parameters if they want to improve the treatment or they want to improve the performance. So the patient needs to go visit the doctor to adjust the stimulation parameters. These three points are very important in the negative side of open loop, conventional open loop DBS. So necessity is the mother of invention, as quoted by from Plato. Like every problem demands creative efforts, and when there is a problem, we work creatively, we put creative efforts to resolve the problem. Of course, as I already mentioned, any problem, there are numerous solutions for multiple solutions for any problem, but we need to identify the right solution depending on the target platform and the required performance. So here comes the concept of closed loop deep brain stimulation, closed loop or adaptive deep brain stimulation. So in the adaptive deep brain stimulation, the stimulation is delivered to the infected, to the target brain region only when the brain is in abnormal state. You know, like when the patient suffers from any motor symptom, there is some abnormal pattern in the deep neural recordings of the brain, and we need to identify the pattern. So if there is some algorithm that could detect the early onset of the pattern, so that we can deliver the stimulation only when the brain is in abnormal state. So it demands it requires a closed loop algorithm for automatic detection of pathological oscillations. So this is the motivation towards my research problem, the next slides will be focusing on the design of algorithm to resolve this problem. So we will see the difference between the open loop and closed loop. In the conventional open loop, as already seen shown in the animation, current is the electrical stimulation is given continuously to the target brain region. Yet stimulation is given directly. And in the case of closed loop DBS, we have a brain-machine interface or a neuroprosthetic, you can call it any name. And the device or sensor that detects the pathological oscillations from the brain, and depending on the pathological state, whether it is it's a pathological or non-pathological, it adjusts the stimulation parameters so that the stimulation is turned on or the amplitude parameters are adjusted based on the patterns, based on the response from the brain. So this uses a feedback from the brain to adjust the stimulation parameter. That's why it's called closed loop deep brain stimulation. So here, recently in 2017, the company, the Neuro Incorporation, revealed their first next-gen responsive neurostimulator system. That is the closed-loop stimulation system to treat epileptic seizures. Here you are going to see the principle of closed-loop deep brain stimulation. So, sorry. As you can see, the stimulator is placed under the skull. The stimulator, there are two versions here. One thing, one option you can place the stimulator under the skull. In the other option, you can place the stimulator externally. That means under the shoulder. So this is the basic principle of closed-loop deep brain stimulation. Though this device is for treating epileptic seizures, the principle is going to be same. The oscillations will be different. The type of pattern to be detected will be different, and the temporal resolution, the spectral resolution will be different. It depends on the disease. So here, the stimulator continuously monitors the brain waves, and if there is any pathological abnormal state, it delivers stimulation. Otherwise, there is no stimulation. So you could see the local field potential here. On detecting this one, it delivers stimulation, so that the stimulation is. So you could see the stimulation relieves the motors, pathological, resets the pathological neural oscillations. And this is the main purpose of stimulation. And these oscillations might be related to the motor deficit in epilepsy. So 3 steps: monitoring, and then detecting the pathological state, and then delivering the stimulation. And patients can collect data by telemetry from the device to their laptop or the software provided by the company. So this is the device which you have just seen the principle of the working of course of this device. So this is for treating epileptic seizures. So each neurodegenerative disease, each disease has different symptoms and different frequency bands and shape and the temporal resolution. So here you are seeing and we'll just see the architecture of a responsive neurostimulator system. I'm going to explain because as I already mentioned, the solution is very simple, but we should be very careful in selecting the right solution, and the right solution depends on the requirements hardware platform. Depending on the target platform, you're going to deploy the algorithm. So here I'm going to explain the target hardware platform. So as seen from this figure, the Neuro, any closed loop DB system is implemented using the microprocessor or microcontroller because the device has to be compact and low power consumption. These two criteria is very important. And the microprocessor, we know the limitations of microprocessor. So that algorithm we are going to provide to resolve this for the particular problem has to be deployed in the microcontroller. This is very important, microprocessor. So we should develop an algorithm that is hardware friendly for microprocessor. This point is very important. That is why the topic is computationally efficient early detection of oscillations. Because there are, as I already mentioned, there are multiple things. You can use a deep learning, or you can use a machine learning. You can use wavelet transform. There are many multiple solutions, but the solution has to be implemented in the microcontroller. That is the challenge here. So I'm coming back to my research problem here. I'm going to show you the characteristics of a Parkinsonian rat model. The characteristics of a Parkinsonian rat model. So we will see the characteristic signature of Parkinsonian symptom, and then we will proceed to the algorithm. So rats under normal condition, they are free to move here. There is no any abnormal movements from the rat. But suddenly they find they have some kind of movements of very involuntary. So that shows the characteristics of a Parkinsonian rat. This rat is the Parkinson is induced as a Parkinsonian rat model. So under normal condition, you see that here the local field potentials are seen here. Just so it's random and low amplitude oscillations are seen. But during spindling, you see the abnormal or involuntary movements, series of involuntary movements. You could see the oscillations are very large amplitude oscillations, and as well as it has some rhythmicity compared to the non-pathological state. Okay. Before going further, let me explain what is local field potential. Actually, neurons communicate with each other through the membrane potential. It has some through action potential, but through spiking activity, they communicate between with the neighboring neurons. And here you are seeing the local field potential. Local field potential is the average electrical activity of a small population of neurons, maybe some hundreds of neurons in the region. Parkinson disease important. One of the important main characteristics of Parkinson disease is the hypokinesia. That is the difficulty in movements, and you could see these oscillations are associated with the movement deficit in Parkinsonian disease. It is reported in many research articles, and especially in Parkinsonian rats. And these oscillations are called high voltage spindles. You could see the pathological state. Under normal conditions, there is no, the oscillations are quite random with low amplitude oscillations. But during the pathological state, high voltage spindling state, you could see rhythmicity, and moreover, these are non-stationary because their mean is different from the background activity. So we understand two important characteristics. The high voltage spindles have spike and wave, and they have different shape. That's very important, and they are non-periodic. They cannot judge the period of the occurrence of high voltage spindles, and moreover, they are non-stationary compared to the background activity. You could see other important characteristic is you could see the spike and wave oscillation. There's a waveform as well as have some such spikes, and moreover, they vary widely in amplitude across brain regions and different subjects and different rats. So the research problem here, you can see I just brief the research problem in the form of 4 objectives. We need to formulate a frequency selective predictive model. I will tell you, like I will explain you, justify the statement in the later stage why we need to go for predictive model. First, we'll visit the conventional techniques, and then we'll move to the necessity or requirement of a predictive model. We need to formulate a frequency selective predictive model to learn the features of high voltage spindles from a very short data, because this is very important. Because if it learns from long data or long period of data, there is no necessary for this algorithm, because finally it's going to be deployed in a low power device that does not have any large memory constraints. They have more memory constraints or hardware limitations, and we need to develop a computationally efficient model based algorithm. Using this model, we need to develop an algorithm for early detection of high voltage spindles. And finally, there is the algorithm in 8-bit microcontroller. We all know the limitations of 8-bit microcontroller. So that is why it has to be computationally efficient. At the same time, it need to detect the early onset of high voltage spindles and evaluate the performance on recorded LFPs. And finally, demonstrate the algorithm as a smart Neuro stimulator for suppressing high voltage spindles by closed loop device. This is the final ultimate aim of this experiment, to show the applicability of the algorithm, proposed algorithm, as a smart Neuro stimulator that could be able to suppress high voltage spindles by closed loop DBS approach. So this is the research problem in a simplified view. Okay, let's visit the conventional techniques, and then we'll we'll find the reasons to move to the predictive modeling approach. Using Fourier transform, we could see we could compute the power spectral density. We could see the spectral features of high voltage spindles. As reported in the literature, the high voltage spindles has oscillations between dominant oscillations in the range of 5 to 13 Hz. You can see, if you apply the Fourier transform to this located spindling LFP, you have the power spectral density here. Of course, the dominant oscillations are around 7 Hz. Of course, it could span any frequency in the range of 5 to 13 Hz. For this high voltage spindles, the dominant oscillation is about 7 Hz. But when we apply this Fourier transform over the different high voltage spindles from different regions and paths, we find that the dominant oscillation is around 7 Hz. Dominant oscillation. Of course, they may have multiple peaks in the 5 to 13 Hz, but the dominant oscillation is around 7 Hz. So the main characteristics of high voltage spindle include, we know the spike and wave pattern. We already know from the temporal representation. We have the high voltage spindle exhibit a beautiful spike and wave pattern, and the oscillations are in 5 to 13 Hz range. Spectral features. So we can, how about detection algorithm based on the Fourier transform? We know very well, because in the previous slide we noted that the high voltage spindle exhibit a higher power in the 5 to 13 Hz. But one thing we all know very well is the Fourier transform lacks the time information. It provides only the spectral information. Of course, we can use short-term Fourier transform by using a window, and we can use an overlapping sliding window. We can, for example, we can divide the LFT into small segments, and we can slide after 1 millisecond, or we can use this algorithm. But I will tell you what is the reason. What would be the impact in the performance? So here you could see that in many of the closed loop devices, they use the Fourier transform to compute the power. For example, here we're going to see the relative power spectral density. The difference between PSD and relative PSD, because we know very well the LFPs vary in amplitude and frequency across the brain region. So it is important to select a metric that is robust to noise, that is robust to the variations in amplitude and spectral features. So that is why we select a relative power spectral. It's nothing but the ratio of the power spectral density at a frequency divided by the total sum of the power spectral density in the range. For example, if you're considering the range of 2 to 35 Hz range, then we need to sum the denominator should be the sum of the PSD, that is the total spectral power. And the relative HVS power is nothing but the sum of the relative PSD in the 45 to 13 Hz range. This can be used as a detection threshold criteria parameter to detect the occurrence of high voltage spindles, as explained in this algorithm. We can use an overlapping sliding window. We can divide the LFPs into shorter segments, and we can compute the relative HVS power for each LFP segment to detect whether it is a HVS or not. But still, the problem is the resulting precision and latency are not sufficient because we know very well it's due to the non-stationary behavior of the high voltage spindles, because we cannot judge the occurrence of high voltage spindles in the window or the selector window or something. We can approximate, but there is some limitation. There is a limitation of Fourier transform. Of course, we can improve, but the improved performance is still not sufficient for the real-time detection. That is what we found by applying the Fourier transform over different over the LFS from different brain regions and different rats. Next solution is we need time information and frequency information at each time instant. So we can go for continuous wavelet transform. So continuous wavelet transform, by using continuous wavelet transform, we can compute the time frequency distribution that shows the features of the signal in the time frequency plane. That is very efficient. That is very helpful to analyze the signal offline. We will see the algorithm here. So here you're seeing the for this continuous in any wavelet transform, the wavelet shape is an important parameter. So during my pilot study, I designed the custom. I designed the complex Morley wavelet according to the spectral features of the high voltage spindle. This algorithm is based on the complex Morley wavelet designed for this custom designed for this high voltage spindle. So here it shows it displays the time frequency distribution of the high voltage spindles. So you can see during the spindling, for example, consider the occurrence of high voltage spindle between its marked by the indexes T1 and T2. During T1 to T2, the energy is very high. So you could see the colors are mapped from lower to higher values. White represents the lower value, and black represents the higher maximum values of wavelet energy. So during the occurrence of high voltage spindle, the wavelet energy is very high. It displays higher wavelet energy, and you could similar to the Fourier transform algorithm, you can sum the wavelet energy in the 5 to 13 span, and you can use this as a parameter to predict the occurrence of high voltage spindles. But still, I will later show the other side of continuous wavelet transform, demerits of continuous wavelet transform. Of course, it's very useful for the analysis of high voltage spindles offline. Okay, this is my algorithm I designed during my pilot study. Just windowing we can divide the LFS into small segments, and here during my pilot study I did not use the overlapping. I just used the non-overlapping to just see the features of continuous wavelet transform. It worked very well, but of course it resulted in higher detection latency. It is expected because it is the result is this performance is based on non-overlapping windows. Of course, we can reduce the detection latency by using overlapping sliding windows and with the reduced slide factor. I will show you the benefits, merits and demerits of overlapping windows with continuous wavelet transform. The detection latency could be decreased by overlapping sliding windows, but it is computationally more expensive. For example, the CWT-based detection algorithm takes 600 seconds. The time, see the algorithm, this computational time is the time taken to process 1 minute long LFPs with this window parameter. That is, window length is 512 milliseconds and the slide interval is 1 millisecond. Of course, you get good results, but the problem is it is computationally very, very expensive. It takes 600 seconds to process 1 minute long to process just 1 minute long LFPs on the Intel CPU. So we can increase the separation between the windows from 1 millisecond to 24 milliseconds. It takes 26 seconds. Still, it takes 26 seconds, and also it achieves sufficient detection performance for our application. But the problem is regarding the hardware implementation in microcontrollers. Again, it is not the wavelet is not the continuous wavelet transform is not. It's still not hardware friendly for resource constrained systems such as the low power microcontrollers. And moreover, we designed the wavelet based on to match the spectral features of the high voltage spindles, the target signal or features. So sometimes I already mentioned the high voltage spindle, we cannot expect the same shape across the brain regions and different subjects. It's highly variable. The wavelet shape is highly variable. So sometimes if the due to some higher background noise, if the shape of high voltage spindles is affected by noise, the continuous Wavelet transform might not give good results. It results in poor precision and also higher latency for those LFPs with the higher background. This is a demerit of two demerits of algorithm. Still, it takes higher computational time and the wavelet shape. So, what can be the other techniques? Okay, here comes the importance of predictive modeling, combining predictive modeling and fast Fourier transform. We know the importance of fast Fourier transform. Fourier transform gives good results, satisfactory results with stationary data or stationary signals. But we have in the high voltage spindle, we are non-stationary. So the solution is the problem. How we can offer the solution is how we can able to approximate the non-stationary HVS as a stationary HVS. This is the solution. So for this purpose, we are going to use the predictive modeling to approximate the non-stationary high voltage spindle as a stationary signal within a particular time scale. So I'll go with the statement of Dr. George Box that all models are wrong, but some are useful. We cannot expect a model to completely represent the system, especially when you come to the highly complex brain central nervous system. It's very difficult to describe in terms of model, but you can use the model that could describe the target features. Here, in this problem, our target is to detect the high voltage spindle. So you could devise a predictive model that could learn only the features of high voltage spindles, because here I don't care about the non-HVS oscillations. I mean, if it is, I just care about whether the segment is HVS or not. So if I learn the features of high voltage spindle, I need to design a frequency selective model. So that is the purpose of autoregressive modeling at interval. So you can select the two important parameters of model are P star, this P asterisk, the model order and the sampling time lag. So here you can see the equation here. So Xn the left side represents the estimated signal at time n, and the right side shows that the signal is estimated from the previous samples that are scaled by the weight coefficient, the model coefficients, that is Wi. So you can, this is the basic, as I already mentioned, the solution is very simple, but you need to prove that this model is sufficient to represent the high voltage spindles, and we can able to devise an algorithm using this model. That we will see. The important, this model order is very, very important, because the model order determines the number of determines the spectral resolution, and it can be learned by this model. The Kalman filter can be used to learn the model coefficients from the training data set, and we'll use the offline learned model in the algorithm. So as I already mentioned, we need to approximate the non-stationary high voltage spindle locally stationary stochastic process from the autocorrelation. These two concepts are very important to determine these parameters: model order and sampling time lag, autocorrelograms and partial autocorrelograms. So autocorrelograms is nothing but autocorrelation functions of different LFVs, and partial autocorrelograms, I will show you the impact of what are the results we can take from autocorrelograms and partial autocorrelograms. So this is the figure A shows the autocorrelation functions of different LFPs, bandpass filtered LFPs. Before computing autocorrelation, the LFPs are bandpass filtered in the frequency range 5 to 13 Hz, because we know very well the high voltage spindles the spectral features of high voltage spindle is observed in the 5 to 13 Hz range. So that is why we use the bandpass filter in the offline learning algorithm. The bandpass filter is used to filter the features in the 5 to 13 Hz range. The filtered signal, then we compute the autocorrelation over the LFPs. This plot shows the autocorrelograms of 8 LFPs, 8 set of LFPs from different brain regions of 3 Parkinson rats. So you could see on an average, the first peak, this is the value of autocorrelation is 0, and the first peak appears around 143 milliseconds. So this first peak indicates, if we select this, this indicates we could see, and if you use this value as model order, you could see the high voltage spindle can be predicted very well, but still it is higher order. So if your signal is estimated from 143 previous samples, of course, it's not computationally efficient, right? So we need to go for a low dimensional model. That's why we use a partial autocorrelation to see the features required for us. And here you could see in the partial autocorrelation, the model order at the value of 6, you could say, even you can also say the value of 5 or 6 or 7, but 8 is it almost touches the confidence interval. You should select the point that is just far away from, it is close to the confidence interval, but you should not touch it. So you can evaluate the model performance using 4, 5, 6, 7 with the model, and you can use the normalized residual and the relative error variance to judge the performance of the model. So based on this, we can select the model parameters. So this is the architecture of the proposed one, and here basically we can design offline learning algorithm and online learning algorithm. The offline learning algorithm is based on conventional Kalman filter, and the online learning algorithm is based on adaptive Kalman filter. This Kalman filter is a very it appears to be simple, but it takes a lot more time to understand the concepts and to identify the right parameters for the Kalman filter. The concept is very simple. When we give the input sample, small segment, say for 144 millisecond, the learned model has to predict the rest of the learned model, the offline learned model has to predict the LFBs, so that the LFB segment is extended to 512 millisecond. Then we can use a Fourier transform based HVS detector to compute the HVS power, relative HVS power, to detect the occurrence of spindle. In this case, in the offline learning algorithm, when we use the trained offline learned model, it just predicts it approximates the predicted samples will be close to the stationary components of the high voltage spindle. So that's why in this case the Fourier transform gives good acceptable sufficient performance when compared to the isolated Fourier transform. So I don't go to details, mathematical details of Kalman filter, but the thing is, concept is it has two components. One is the update predict component, and another one is correct component. First, it estimates the several values, and then it is corrected from the by inputting the local field potential values. So I suggest we want to go through the reference article at the end of the session to study on the mathematical concepts of Kalman filter. So here, it's again an important point to be noted. So I just compared the execution time, the time taken to process the 1 minute long local field potential among the different algorithms. You could see, of course, CWT takes with the value of slide interval of 1 millisecond, it takes 600 seconds, but offline learning algorithm, it takes only 1 second, but it results in acceptable performance as shown in the next page. But you can also decrease the DL, the separation between windows to further. But you could see the computational time is increased by a factor of 19 here. So we need the acceptable performance, but with the computationally efficient algorithm. That's why the offline learning algorithm is suitable. Of course, you can get the superior performance with the online learning algorithm, as will be shown later. But in the case of Fourier transform, the performance is very poor. Even though we select a window length of 512 and 1 millisecond, still the performance is poor in terms of precision and latency. Of course, this takes only very less time, but the performance is not sufficient for the real-time implementation. So this shows a comparison of among the different algorithms. So this is a typical high voltage spindle episode. So you could see the results of different algorithms. B shows the relative HVS power computed by offline learning algorithm. C is the continuous Wavelet transform, and D belongs to the online. D belongs to the continuous Wavelet transform. So you could see how each algorithm detects the early onset of high voltage spindle here. Online learning algorithm, it detects the HVS earlier than the other two algorithms. You can see the time index TC based on the setting threshold. Threshold varies from among the different range regions and rats. And continuous Wavelet transform, even though it takes a window length of 512 samples, still, as I already told you, due to the window wavelet shape or the noisy factor, it results in higher latency when compared to the other two algorithms. So when we are proposing any algorithm, we need to evaluate the algorithm on huge or sufficient data set. So here I'm showing you the result of the performance of the different algorithms on 1088 HVS episodes that are recorded from different brain regions of 3 Parkinsonian rats. You see the performance. If you take the performance I mean recall, precision, and edge score. The this in the 3 metrics are relevant to the detection performance of the algorithm. The performance has to be higher. These metrics have to be higher. In terms of performance metrics, all the 3 algorithms are comparable. I would say comparable, even though the superior performance is achieved with online learning, because in the online learning algorithm, the parameters are varied instantaneously. While in the offline learning algorithm, we learn the parameters offline and then use the learned parameters in the prediction phase. And also the latency, even I would say latency also is still comparable, but in terms of execution time, I mean computational time, the offline learning is the most computationally efficient. Especially this offline in this simulation study, I used the window length is 512 millisecond and the separation between windows is 24 millisecond. But in the real-time implementation, I downsampled the LFPs to from 1000 Hz to 42 Hz. Then I use the window length is 6, and the Fourier transform uses 16 samples to compute the spectral power, HVS power. So here we are going. I'm showing the real-time detection performance of the offline learning technique. So it shows the first plotting A shows the non-spindling, the local field potential, real-time local field potential recorded from the brain region. It's the rescaled input, because we need to, in the real-time implementation, we need to consider how we are going to process the LFP. For example, before resampling, we should know how to give the input to the microcontroller. Microcontroller accepts the input in the range of 0 to 2, depending on the type of model of microcontroller. It varies, of course. So we need a signal conditioning circuit to rescale the local field potential, and then the third plot in C shows the detection response. For example, for the non-spindling, the response should be low, 0, low. It should be low. Otherwise, it should be high. It should be 0. And during the non-spindling LFP, there is no stimulation pulse. So when the algorithm is used, when there is on detecting the high voltage spindle, the pulse, you should see a response from the pulse stimulator like this. So here in C, the values, the plot in D shows the output of pulse stimulator. The stimulator goes high only when the detection response goes high. So otherwise there is no stimulation from the pulse stimulator. So this is the basic concept of the closed loop deep brain stimulation. And so this is a block diagram of how we are going to use the algorithm in real-time implementation. As I already told you, we need a signal conditioning circuit to condition the real raw local field potentials from the rack. So local field potentials are recorded and then amplified, and then we given to the microcontroller after the signal conditioning circuit. For every 144 milliseconds local field potential for every 144 milliseconds, and the local field potentials are resampled to 6 samples. From the 6 samples, the model predicts the next succeeding 10 samples. So with a total of 16 samples, the Fourier transform is computed, and the whole computation takes less than 1 millisecond. That is the sampling time of the local field potential. This is very important. We need to complete the the computation time should be less than the sampling time, so that it may not affect the accuracy of the ADC. So I'm going to show you the real-time detection performance in this video. So the algorithm is basically implemented on a microcontroller, and this is going to be the signal conditioner circuit. Signal conditioner takes input from the raw LFPs. Here, the real-time computed bandpass HVS power is shown in on the laptop. You can see the real-time detection performance of the offline learning algorithm here. So the important thing is the algorithm should be able to detect at the early onset of high voltage window. That is very important so that the stimulation curve can be turned on and there can be high voltage window can be suppressed. In this case, the stimulation is not connected to the brain region, but we have also tested the stimulation, how the stimulation controls the high voltage window. This is the real raw LFPs recorded from the rat, Parkinsonian rat. And this is a rescaled local differential, the output of the microcontroller. The output of microcontroller is used as a trigger to the pulse stimulator, so that on detecting the high voltage spindle, the stimulator is turned on. And more importantly, during the non-spindling, you should not see any pulse output, stimulator output, and that affects the precision of the algorithm. And it generates more false positives. Two criteria are very important here. One is how accurately it is detecting the high voltage spindle, and the another thing is equivalently how accurately it is able to differentiate between HVS and non-HVS, because these two criteria are important to determine the performance of any algorithm, I would say. And apart from that, in this context, we need a computationally efficient algorithm. That is why we use this approach to improve the temporal resolution of this. You can give this technique as a improving the temporal resolution of Fourier transform by using predictive model. It predicts the if we apply the Fourier transform with the window length of 1, just directly without any predictive model, the result will be very poor due to the lower temporal resolution. So in conclusion, compared to the conventional techniques, the predictive modeling approach helps to detect the event or a required feature at the very low computational efficiency, very low computations. And moreover, the important thing is from the real-time implementation that HVS is detected just from 6 samples. Just from 6 samples, it detects it. Then using the predictive model, it predicts the succeeding 10 samples. So with a total of 16 samples, Fourier transform is applied. And the result in the real-time implementation, you get the result of about latency is lower, less than 150 milliseconds. And this result is not be possible with the previous without a direct predictive model, or even when we use the continuous level transform also in the simulation, you could not achieve this if you are using with the resample signal, because when we resample the local potential and the wavelet shape may be affected. So finally, the closed-loop DBA system could be this proposed algorithm could fit the requirements of smart neurostimulator to realize the closed-loop DBA system. So with this approach, we can be able to suppress the high voltage spindles that may help to relieve the motor symptoms impairments in Parkinson's disease. So here I complete my presentation, and the references are mentioned here. I suggest you to go through because I would say I also we learned the subject during my undergraduate. I learned the subject called statistical signal processing. I learned the Kalman filter, but I missed the beautiful beautiful aspects of Kalman filter. They were hidden in the almost hidden in the text actually. You need to uncover it. So I would suggest you to go through. There are many texts, of course, but you can also view this PDF. Hope it would be a good start to learn about the Kalman filter. Kalman filter can be used has been used in many applications from the aerospace industry to brain-machine interfaces to many applications, and it's very optimal for real-time implementation in FPGA or high-end microcontrollers. So I observed some questions here. Let me go through one by one. would start from, is the stimulation AC or DC? What is its features such as hertz and millivolts? Yes, the electrical stimulation has to uh, has to has some different certain characters. For example, the it, the stimulation has to be 130 hertz, and the voltage depends on the hello.
Yeah. Hello.
Sir, thank you very much for. I'm Dayashini, sir. Hello.
Yes,
Thank you very much for a very informative webinar by showing the videos of real-time detection, sir. Sir, I have a question. How early we can detect the symptoms of Parkinson's disease using this predictive modeling?
Actually, using the current setup, we from the simulation we could able to detect with the latency of just around less than 80 milliseconds. In the real-time case, for example, in the real-time case, we have a lot of optimizations. So in the real-time case, we can detect with the latency of 150, less than 150 milliseconds, less than 150 milliseconds.
Okay, okay, sir.
This is the latency.
Okay, yeah, okay.
Yes, sir. I think we have some questions in the chat.
Sure. I will just I will just read one by one and respond.
Yeah, I think we answered the AC or DC and hertz and millivolts.
Yeah.
Yeah.
And
the next
predictive
question.
model, is the latency important as you want? Yes, the latency is very important because with the continuous Euler transform or Fourier transform. Okay, let's take the Fourier transform. With the isolated Fourier transform without any predictive model, it achieves the latency of around less than in the range of 200 to 300 milliseconds. But still, we want the latency to be lower so that we can able to suppress the symptoms earlier. Because if we compare with different diseases, different temporal resolution, compared to epilepsy, Parkinson disease is quite spontaneous. I mean, the temporal resolution is very low, and we need to detect very early so that we can avoid the symptoms. And how do we get the golden truth? Okay. Hello, Professor.
Yes, sir. Please go ahead.
Udupi Niranjan. Hello, Dr. Udupi Niranjan. Golden truth can be generated by using Hilbert-Huang transform. Because compared to Wavelet transform, of course, we can also determine the time frequency. We can use continuous Wavelet transform to generate the time frequency distribution. We can use the temporal resolution. But I already mentioned, even though we have the good resolution, still the wavelet shape is crucial. So I used Hilbert-Huang transform to compute the ground truth. How do you do it? How do you do ground truth? Why is the time on to crucial? Okay, why is the time on 144 millisecond crucial when detecting high voltage spindle? Sir, actually, high voltage spindles are absolutely definitely they are non-stationary. There is no doubt in that. But I'm trying to approximate this non-stationary as a stationary signal. Of course, that is why we use the autocorrelation. This 144 millisecond is determined from the autocorrelation plot. I showed you the autocorrelation autocorrelograms of different LFPs. There you have the first peak occurs at 144 around 144 millisecond for different LFPs. That means if you have a window length of 144 millisecond, it could be we can very well approximate the non-stationary stationary. This is just approximation. I'm highlighting. Sometimes, in case if the high voltage spindle did not obey this 144 millisecond or exists beyond this one, of course it can be detected in the next window because we are using overlapping sliding window. Definitely it will be detected in the next window. That's why if the high voltage shape differs in some cases, it takes some additional latency. Prognostic point. Here, there is a question from Mr. Gandhi Madinathan.
Yeah.
Mr. Gandhi Madinathan. How earliness parameters can be measured in case of? Is there any standard scale is to measure? I'm not sure which parameter you are referring to. Whether you refer to the feature or parameter in the sense a model parameter.
Hello, ma'am.
Can you give access to Mr. Gandhi Madinathan? Okay, I will respond to the second question. Is there any optimization process? Early prediction of time series has to address the trade-off between accuracy and earliness. Unlike conventional time series applications that address only accuracy, is there any optimization process available to avoid the two conflicting objectives, namely earliness and accuracy? We need to find a trade-off, sir. Actually, the term earliness depends on your application. For example, in my case, the reasonable latency required is should be less than 150 milliseconds. But in case of epilepsy, it may be less than 1 second, or it may be less than 2 seconds. But in my case, in Parkinson, for the high voltage spindles, considering the temporal resolution of a high voltage spindle, the latency of the algorithm should be at least should be less than 150 milliseconds or at least 150 milliseconds. So it depends on the application and the disease features in the disease. Predictive modeling mentioned about auto-regressive model. I have doubt on the general auto-regressive. Okay, there is a difference between actually there is the difference between the auto-regressive model. How we can categorize place the auto-regressive modeling under predictive modeling, because you can use auto-regressive modeling in two applications, two aspects. First aspect is you can design identify the model after identifying the model parameters, maybe the coefficients or any other parameter. You can apply the model, and you can it can be used to identify the relationship between the different categories. This is one way. Another way, you need to find out the optimal model. That's why I say optimal model for the target oscillations. In my case, the target oscillation high voltage spindle, the model I just showed you is optimal only for high voltage spindle, and it is not optimal for the in the global sense. And you need to use the cross-validate your model using the metrics such as relative error variance or normalized residual. Then only you can confirm that this model can be able to predict the certain features. And moreover, after designing the model, when we use the model in the algorithm, we can see the predicted LFPs, range of predicted LFPs, and the spectral features. Of course, that determine if the model is not optimal, of course, it won't be useful. It won't result in reasonable detection performance.
Yeah, there are a few questions which are sent privately to me. I'll read it out to you.
Sure.
How early Parkinson can be detected as of now?
Neurotransmitters, I have no idea. I have no idea on the neurotransmitter. Because neurotransmitters, I have no idea on the biological, on the bioinformatics process. I'm not sure about that. Another one, sorry, second question. How early?
Yeah.
How early?
Yeah.
Parkinson symptoms vary. Actually, if you see the slides, according to the statistic, Parkinson, the most common age, people over the age of 60 is considered or more prone to be infected with by movement disorders like such as Parkinson's disease. But in recent cases, people under the age group of 30 to 40 are they have also infected. They can also have new cases in the age group of 30 to 40. The symptoms are really very difficult it's very highly variable. So we cannot say, but in some cases, non-motor symptoms appear. For example, people may suffer from sleep behavior disorders or some neuropsychiatric effects. The symptoms are not only motor. So before the appearance of motor symptoms, non-motor symptoms may also appear. So based on that they can measure the. There are some techniques to measure the movement deficits. in humans. Of course, they use the standard techniques to measure how the advanced is the Parkinson disease for a particular individual.
Okay, sir. Next question is why 8 LPF from different regions of the brains are used to autocorrelation calculation?
We have the recordings. It depends on how many regions you have recorded. For example, in our case, we have local potential recordings from 8 brain regions, 8 different brain regions of Parkinson's disease. That's why I use all the LFPs from 8 brain regions. That's why I use 8 brain regions, 8 LFPs in the plot.
Okay. One more question. Can you give more details on Hilbert form transform?
Hilbert-Hong transform is a very promising technique compared to other time frequency distribution techniques. Basically, it employs empirical mode decomposition and Hilbert spectrum analysis. I will give you, maybe I will share some PDFs with you to get to know about the Hilbert transform. Those who are willing to, I highly recommend this technique to analyze any data. The reason is, it does not require any window. It does not require any conditions. The analysis is completely based on the data. For example, if in case of Fourier transform, the basis functions are derived. The basis functions are sinusoidal functions. Okay, but in case of continuous Wavelet transform, we derive the wavelet shape and wavelet function. It depends on the data. We need to design the wavelet shape. But in case of Hilbert-Hong transform, the basis functions are adaptively derived from the data itself on different time scales. That is why it does not require any preconditions. I highly recommend Hilbert-Hong transform to analyze any non-stationary data. It gives good temporal and spectral definitions compared to the Wavelet transform and the Fourier transform. Yes, sir. Hello.
Neuro. You know.
Actually, your voice is a little breaking. Can you please repeat once again? Sorry, your voice is breaking. Okay.
Can you?
Actually, maybe you can type the. Yeah. Please. Sorry, can you please repeat the question once again?
Yeah. Can you hear my voice? Yeah.
I heard, but please repeat the question.
Yeah, I just wanted to know, in which regions, or in which areas our final year students or pre-final year students of engineering can do their research projects on, that is what I was trying.
I highly, thank you. Actually, there are different regions that definitely we can consider, but since I am doing biomedical, I know something interesting to me, and so I would like to share. There are several companies have started their some initiatives. For example, Code for Good by IBM or SGS company, and they expect the participation from students to program to whether it may be related to deep learning or pattern recognition or some good. But from my perspective, that nowadays there are so many freely available data sets from different universities and companies and medical research laboratories. So those who are interested in pattern recognition, deep learning is very hot, and especially I would recommend pattern recognition, or it may be time series analysis or images or video informatics or anything. So you can this data students can use the freely available data sets to implement their own algorithms.
Okay, sir. I think that's the end of the Q&A. If anybody has any other questions, you're welcome to post it on the chat. In the meantime, I request Dr. Yusian to give his comments.
Thank you very much, Mr. Perumal. It was a very interesting talk. You talked about the onset of Parkinson disease, especially in the elders. And we here in India are also an age, though we are said to be the country with the most youngsters, but people are also aging here, like in Europe and Taiwan and USA. So we also have quite a significant aging population and who suffer from problems such as Parkinson disease, Alzheimer's disease, dementia, and so on. So your research is very apt and for even countries like India. And you touched upon many aspects of signal processing and then animal studies and putting everything on an 8-bit microcontroller to make it a viable prototype and product. Thank you very much. It was very, very interesting and you answered to many, many questions. And interestingly, the IEEE MSS webinar, which has been going on for quite some time now, we have had many speakers from abroad, but most are from Taiwan. We had two speakers, speaking to us from Taiwan, and we have alumni of a Taiwanese university speaking to us in one of the webinars. So Taiwan makes the majority of our foreign speakers.
Exactly.
And
it's really good to hear, Professor. Thank you. Thanks a lot for your feedback, and I'm very happy that I did something that may be useful to you.
Yes. And I'm also very happy to note that you have a lady prime minister in Taiwan.
Yes. Yeah.
Yes. And all these ladies who are heading these nations have controlled the COVID-19 to a great extent, be it Thailand,
Yes,
be it
yes.
New Zealand.
New Zealand. Yes.
New Zealand, or be it a few Scandinavian countries. So those are the people, because they make, they deal with family members regularly. They know the triumphs and tribulations of a family. So I was very happy to note that you have controlled COVID-19 very, very well in Taiwan, and you have had no lockdowns at all. That's very, very great. Thank you very much for giving us all this information in this webinar. We hope to have, we hope that you would complete your doctorate very soon. And I also take this opportunity to thank all the esteemed faculty members of SJEC, Dr. Dayakshini, Professor Keith Fernandez, Professor Rashmi Halevane, and Dr. Jagdisha for this arranging this interesting webinar. Thank you very much.
Thank you, sir. Thank you very much. Yeah, we have one last question. I'll just put it forward. Whether Parkinson's can be treated non-invasively using electrophysiological equipments?
Yes. Good. Actually, it's a different category. It's called smart wearables. Smart wearables. We can use smart wearables. We can design. There is also so many research efforts going on in the smart wearables to measure the abnormal movements. But the problem here is, finally, from the various the performance is very perfect with the invasive local field potential based detection detectors. The latency is very less in this case, and the performance is very good in the very optimal in the invasive, local field potential based detection devices.
Okay, sir. I think that's the end of the Q&A. All right. So we will conclude. Thank you very much for joining the session. I think, we approached you and you readily accepted our invitation, and Dr. Jagdish has been a key person in arranging these webinars from Taiwan. So I would like to thank you, Mr. Ramesh, for accepting our invitation and being here with us, spending your time, informing us with your research, what you have been doing. And we hope that you complete your PhD at the earliest, and all the very best for that. Thank you, sir.
Thank you very much. Thank you very much, everyone. Thank you. Thanks for listening to me. Thank you. I'm very happy about that I said something. Thank you. Thank you, guys.
Thank you, sir. So I would also like to thank all the organizers of today's webinar. A special thank you to Dr. Jagdish for identifying the speaker. And I would like to thank our HOD for her constant support. And finally, thanks to Ms. Rashmi, who has been helping us with all the logistics that are required for this webinar. So with this, we will conclude today's webinar. For your information, our next webinar is going to be on the 15th of July. And it will be again from a person who is identified by Dr. Jagdish itself. So it will be on predictive analysis of big healthcare data, keep the disease at bay by Dr. Suvindu. So make sure that you reserve the time. So we will be having this webinar at the same time that we are having today, that is 2 to 3:30 p.m. So with this, I will conclude. Thank you very much. Thank you for joining.
Ramesh, thank you very much.
Thank you, Jagdish. And
Okay.
please feel free to contact me by email.